So why are oceans so important to Australian weather and climate? Well, one thing, it's a sea surface temperature, also known as a skin temperature and radiometric temperature, that tells us about the distribution of heat within the ocean. And that heating of the ocean has an effect on the overlying atmosphere through transfer of water by evaporation into the atmosphere, as well as the transfer of heat into the overlying atmosphere. Sea surface temperature tells us about the condition of the oceans. We know that pressure and temperature and density variations are driven by heating. The heating of the oceans will change the density. So the sea surface temperature is a reflection of the density, and density drives the pressure variations, and pressure variations drives the currents we see. So, and the currents drive the nutrient distributions within the ocean. So a service like that offered by the Integrated Marine Observing System here is a very useful resource for example, the fisheries industry that are interested in knowing where they should deploy their fleets to get as many fish as the industry allows and fish are drawn to nutrient-rich waters, and so they will use a resource like this on a daily basis to see where they should be heading. For our purposes, the sea surface temperature is a key variable in some of the major indicators of Australian rainfall pattern. We'll talk about a couple of these in further detail, but basically it's the temperature that driving the density differences, which drives the pressure differences, which drives the circulation patterns we will see. Do have a look at this report if you're interested. It goes into a bit more detail about the drivers. It's not a long report, and if you are keen to get into the area of climate research in Australia, the NESP, NESP is the acronym for National Environmental Science Program, I think, is a good resource and a good group of people to be familiar with, especially the research that comes through NESP. So remember, anomalies tell us about the variation of a quantity to its climatological or long-term average behaviour. Sea surface temperature for anomalies can have major consequences to how much or little rain we get in Australia. And these temperatures aren't just isolated local phenomena, they can stretch vast range in the distance in the oceans, straddle the whole Pacific Ocean, for example. I've got the El Nino and La Nina conditions here showing cooler or warmer temperature, sea surface temperature anomalies. And we'll talk more about these La Nina and El Nino cycles in the next few slides, but here I'm just showing you the anomaly is a spatial pattern that has large spatial range. So because of the extent of the anomaly, it's typically any anomaly in any given space, a location, or in time by itself is not particularly useful. It is useful when put in a context of its neighbourhood, but in space or time. So we look at the, for example, rainfall anomalies, and we compare it to the previous 100 years. Similarly, sea surface temperature, it's not just what's happening in any given location, but how is it different from other parts. Now, to summarise all that, we typically convert that information into an index, because indices are a lot easier to interpret than the spatial patterns of variations in anomalies. So one of the indicators that we'll talk about is related to this El Nino Southern Oscillation. It's a weather system that spans the Pacific Ocean. It has two extremes, El Nino, which is Spanish for little boy, and La Nina, which is Spanish for little girl. The biggest interactual, the ENSO events are the biggest interannual climate drivers, and their impact is global. And largely it's driven by the sea surface temperature, which you recall drives the evaporation rates, and the pressure and temperature variations in the ocean, and therefore the differences in the currents. So we talked up until now about circulation patterns in the atmosphere, and those have been the three sort of cell models of atmospheric circulation, which run longitudinally along lines of longitude. Here we introduce a new circulation pattern which runs east-west. That is it's called the Walker circulation. And the way this originates is based on the typically warmer air over the equator, which we're familiar with now, drives the low pressure system, which drives convection and the lifting of air. Then through the processes of divergence and transport, they move east-west, in a westerly direction, and descend as the cooler air over the East Pacific. And because trade winds result of the pressure variations across the Pacific and the circulation patterns of the through Coriolis, we get the transport trade winds. So under neutral conditions, ocean currents flow north along South America, bringing cooler waters to the region. Southeast trade winds further cool East Pacific oceans, draw upwelling nutrients, cooler water from the Pacific. In the western side of the Pacific, we've got the warmer waters and a lot of increased evaporation over that area. And of course, sorry, this is the Walker circulation I was talking about. Now, in La Nina years, what we have is cooler than normal waters on the eastern side of the Pacific and warmer than normal waters on the western side near the northeast coast of Australia. Those warmer than normal waters in the tropics lead to increased evaporation and therefore increased precipitation through convection. That circulation pattern is intensified when the cooler air descends. The variation across the Pacific is a lot stronger. Therefore, the trade winds are stronger. And what this typically does for Australia is it increases the rainfall for the region over large parts of the country, and has the potential for increasing risks of flooding. It leads to cooler daytime temperatures and an increased occurrence of the tropical cyclones in the area. In El Nino years, what happens is that Walker circulation is disrupted because instead of those neutral conditions, we have warmer than normal waters over in the eastern side of the Pacific and cooler than normal waters on the west side of the Pacific. What that means, having warmer waters near the South American coast, means that there's an increased evaporation in the region, means increased convection, and it disrupts the circulation pattern by dumping a lot more rain in the central and eastern part of the Pacific. So that means very little rain gets to Australia. So that leads to a higher risk of drought in North and Eastern Australia, potentials for heat wave and prolonged frost seasons because there's clearer nights, but there's also fewer tropical cyclones. So in characterizing the ENSO events, we look at the sea surface temperature variations between 2 points in the Pacific, and these are deviations from their normal conditions. We also have this Southern Oscillation Index, which is the pressure differences between Darwin and Tahiti. So we look at the pressure variations. Remember, that's driven by the overlying atmosphere, which is, of course, driven by the sea surface temperatures. And this index shows cycle. Oops. Cycle. In blue, we have La Nina events, which broadly means more rainfall for Eastern Australia. And then El Nino events, which is the negative Southern Oscillation Index in yellow, showing that these are the years of decreased rainfall for Australia. And so in the middle here, between 2000 and 2008, this is the Millennium Drought that you will have heard so much about and lived through. Yeah, so it's all driven by sea surface temperature anomaly and its impact on the overlying atmosphere. So in La Nina events, that's where we have the cooler than normal waters. Here's the anomaly map of sea surface temperature. Don't know when this is for, but we see the cooler than normal waters across the Pacific, the warmer than normal waters in the north of Australia here. There's intensified circulation, Walker circulation pattern driving increased rainfall in Australia, and that of course affects most of Australia here by increasing the rainfall. In El Nino events, the warmer than normal waters extend far across the Pacific, a lot more evaporation across the Pacific, so Walker circulation is disrupted, and so there's a lot more dumping of rain in the Pacific Ocean. Very little of it gets to Australia. So that decreased rainfall affects most of Eastern Australia, a little bit of the Northern Territory.